Hello students, just a very quick video today to talk about the speed of sound. Not the Coldplay song, but go listen to it if you feel like it. So, how fast does sound travel? Well, pretty fast, but not nearly as fast as light. Light is basically instantaneous. There's no way we can possibly see how fast light is moving with the naked eye. But, and not that we can't really see it with sound because we can't see sound, but we can actually observe a delay in the speed of sound. So that's what echoes are. Um, so when sound bounces off something that's far away, then you hear a delay before you hear the sound again. So obviously the speed of sound is fast, but not so fast that we can't actually observe some sort of lag time. Another good example is when you go to a sports game of some sort. Baseball is probably the best example. If you're at a baseball game and you're sitting, way up in the 500 level, far away from the players, then when a batter hits the ball, there's the crack of the bat. It's very loud when the bat hits the ball, and you see it, a split second before you actually hear it, because the light travels so much faster that it reaches your eye instantaneously, but the sound goes slower, and so it takes a little bit longer for the sound to reach your ears. So, how fast does sound travel? The short answer, 343 meters per second. So just picture that at the baseball game example. You're sitting, let's say, if you're sitting way up as far away as you can possibly be from the batter, you might be a couple hundred meters away from where the bat is actually hitting the ball. So it might take more than half a second if sound is traveling at 343 meters per second. Or I don't know, picture yourself, let's say you're hiking somewhere, you're in like the Grand Canyon or something like that. These are like large spaces. And so um, the canyon wall on which the sound reflects and comes back to you. So first of all, it can be pretty far away from you, and not only that, but it's not just the distance that it is away from you, but it's double that, because the sound has to go over to the reflection wall and then come back. So it's doing that distance twice. And so, yeah, you can imagine that that it's traveling pretty far in order to go reflect, come back, and reach your ears again. And so the amount of time it would take is sometimes significant. Another example is thunder and lightning. So you see lightning before you hear the thunder, and that's another example of the speed of sound. So the light travels faster, the the sound takes longer for you to hear it, and that's why people always talk about how close is the storm. Well, you can kind of figure it out by looking at the delay between the lightning and the thunder, and you can calculate now you can like actually quite accurately calculate how far away that strike of lightning is. In fact, a good way to do it, next time there's a big thunderstorm, you should try this. What you can do is you can just turn on your phone and start filming, or start a voice memo, start recording. Actually, I guess that wouldn't work because then you wouldn't have the lightning. You'll probably have to film. So you film it, and then you wait for the next lightning strike. Then you go back into your video footage, and then you should be able to very accurately trace through the footage, and mark the lightning, mark the thunder, figure out how much time was between them, and then use this formula to calculate the time. Now, hang on a second. Wait. That's actually not totally correct. So the speed of sound is not always 343 meters per second. It depends on some things. It actually depends on a few things. We're only going to talk about one main thing for today. That's what's because some of these factors are more complicated. But just think for a second before I actually tell you. What factor of the air or the environment do you think can affect the speed of sound? Remember that sound is collisions of air particles. So it might help if you've taken chemistry, but um, if you think about the way that particles kind of collide with each other, and if you think about how fast they're moving, like think about what factors can affect the properties of the particles of a gas. So what in the environment can actually change the speed of sound? And the answer that we are going to talk about right now is temperature. So here is a more accurate, more precise formula for the speed of sound. 331 plus 0.6 T, where T is the temperature in Celsius. Now you might be thinking, okay, hang on, 331, the number we were just looking at was 343. So what's going on here? So this number is actually the speed of sound approximately at room temperature, so about 20 degrees or something like that. And that makes sense if you plug that into the formula. So if I put in 20 for T, 20 times 0.6 is 12, plus 331 is 343. So yeah, that's exactly at 20 degrees. If the temperature is 0 degrees, then the velocity of sound is only 331. So it's slower in colder temperatures. And that makes sense because if you know a little bit of chemistry, you know that when temperature is colder, the particles are moving slower because they have less energy. And so the collisions of particles are happening less frequently. And so sound is not able to, I can't think of the right word. It's not able to propagate. It's not able to propagate through the air as quickly when there are fewer collisions of particles. So that is a more precise formula for the speed of sound. Now this is just a modification where we use Kelvin instead of Celsius. Remember that Kelvin is just starting from absolute zero, which is negative 273 degrees Celsius. So it's actually just taking the Celsius scale and just shifting it down by 273 degrees. So and I'm not going to show you the formula for Fahrenheit because who cares about Fahrenheit? We shouldn't be using Fahrenheit. Forget Fahrenheit ever existed and never use it again. Okay, I think that's it. Now you have some questions to do. Enjoy and go out and observe the speed of sound in your life.